Okay, so we're going to get started now with problem 7.21 from the book. We're doing 7.21 and 7.22. They're all pretty similar problems here. They just involve this angled beam here, and they want us to find the internal forces at this point J here. So to get started, we always just want to do a free body diagram of the entire beam. So I'll do my best here. So we're going to have some reaction here. We'll call that AX. We have this force down P here. And then at D, since there's a pin, there's going to be two reaction forces. So we'll just call that dy and dx. Okay. And all of these dimensions here are just given in terms of this length A. So that makes it a bit easier to solve for moments. We don't have to do any actual numerical stuff because it's in terms of A. So to start off, just some of the forces in the X is equal to dx plus AX is equal to 0. Some of the forces in the Y is equal to dy minus P is equal to 0. So we know dy is equal to P. Now we need a moment equation to get our last two forces, or last two reactions there. And I would say we want to do it about point D, since there are two reactions there. It's just going to be easier. So this force P here, if you do a right-hand rule, that's going to give you a positive moment, and it's just A distance away, so P times A, and it's positive. Now this AX, on the other hand, is going to give you a negative moment, so minus AX, and this time it's 2A away. So that's equal to 0. We can just cancel out the A's, and we get AX is equal to P over 2. Okay, and so now we just plug that back into our first equation here, and we find dx is equal to negative P over 2. Now to find the internal forces at J, all we're going to do is cut the bar at J. So we draw that free body diagram. Okay, so this is point J. Let me just move this off to the side. Oops. Okay. Yeah, we want J just written off to the side here, so it's out of the way. Then this is A. And so we know at A, the only force there is AX, which is P over 2, so I'll just draw that in. P over 2 there. Now we're going to have the internal forces due to cutting this are going to be, there's one that's axial, there's one that's shear, and then we're going to have a moment. So it doesn't matter which direction you draw these, just pick a random direction. There is no tension or compression or anything, it's just whichever direction you want. Okay, so if we do some of the forces in X, we're going to get B minus P over 2 is equal to 0. So that gives us our first solution here, B is equal to P over 2. Some of the forces in the Y, well, the only force in the Y is F, so we can say that's 0. So that's our second solution. And now we need a moment equation. So we want to take our sum of the moments about point A. And this is going to give us, let's see. So we have a negative moment due to this force B. So negative B times, it's a distance A away. So negative BA. And then M is also negative. So negative M is equal to 0. It's negative just because of the way I drew it. If you put your hand in the direction that I drew V, your thumb will be pointing into the paper, into the board, and so that's negative. So if we add this here, we end up with M is equal to negative VA. So if you drew it the other way around, you would just get a positive value, but obviously it would just be going the opposite direction. So that's our last solution there. So that one was pretty simple. These next ones add a little bit of complication here. So in this case, our roller is now being supported at an angle. And so we need to figure out what angle the reaction due to that is going to be. So to first, look at this. Okay, so we have a 3, 4, 5 triangle that's supporting it, and we know it's going to produce a force that's normal to this, so we know this is the right angle. How do we figure out what angle this is at? Well, if you remember from any math classes you may have taken about graphing functions, you can write this as a slope. So it's it would be 3 over 4, or I guess it would be negative 3 over 4, we'd be going down 3 and to the right. And to get perpendicular to this, you're just going to do the opposite reciprocal. So the perpendicular is just you take whatever the slope was, you do the opposite, and then the inverse. So this gives us, let's see, it would give us 4/3. So drawing that, we know that means it's going to be going over 3 and out 4. So that's simply how you find the angle that this force is going to be acting at. So now that, let's draw a free body diagram of the entire thing. So now we know we have this force acting here. We'll just call this force A, and it's acting at a 3, 4, 5 triangle like that. So over 3 up 4. Let me just draw it a little better. Okay. We saw the force P acting here, and we're going to have two reactions at D. So dy, dx. So again, we just want to do our sum of the forces. So sum of the forces in the x, we'll have 3/5 ax plus dx is equal to 0. Sum of the forces in the y, we're going to have 4/5 ax minus p plus dy is equal to 0. And so now again we need another moment equation here. And it doesn't matter if you take it about point A or point D. I think I'm just going to take it about point D. So yeah, about point D. So we're going to have a positive moment due to P, so that's P times A. And then the Y component of A is going to give a negative moment. So negative 4/5 A. Sorry, this is a fraction, just make that clear. Negative 4/5 A times, this is the force A times the distance to A. Okay. And then the other component there is going to give a positive moment due to a right-hand rule. So So plus 3/5 A, and that's also a distance 2A away, is equal to 0. So all of these A's just cancel out, and we're left with A in terms of P. So let's just check this on a calculator here. So let's see. So it's going to be 4/5 times 2 minus 3/5 times 2, and then we're going to divide P by that to get A. So A is simply 5/2 P. And so now that we have that, we can solve the problem by doing similar things to the last problem. We're just going to draw or cut it at J again and draw this free body diagram of that section. So again, we have this force F, we have a shear force V, we have a moment M, and then we have this force down here, which is 5P over 2. And again, this is at a 3, 4, 5 triangle here. So we do our sum of the forces in the X, we get V plus, let's see, and the X is the 3/5 times 5P over 2. So the 5's cancel. So it's just plus 3/2 P. This is equal to 0. So then we get V is equal to negative 3/2 P. Okay, so that's our first solution there. I'm going to move over a little bit. I'm going to do forces in the Y. That is going to be F plus 4/5 times 5P over 2. So the 5's again cancel, and we're left with just plus 2P here. So F is equal to negative 2P. Just scroll down a little bit here. So now we want the moment equation. So our sum of the moments about point A is equal to, so again, it's going to be this force V is creating a negative moment, so negative A, but then the force V is actually going in the negative direction, so it's going to turn out to be positive here. And then minus M is equal to 0. So M is simply 3/2 PA. So there's solutions there. Now one more problem similar to this. So now we're just going the opposite direction. So again, let's figure out what angle this is going to be acting at. So we have a 3, 4, 5 triangle. This is a slope of 3/4. So to get the perpendicular to that, we just do the opposite reciprocal. So this is equal to negative 4 over 3. So if you're drawing this out, that's 4, that's 3. 4, 3, going in the negative x direction and in the positive y direction. That's why it's, oh no, sorry, I drew this wrong. Okay, so actually the negative here, the negative can go on either one of the two terms, so it's technically 4 over negative 3, because you're going negative in the x direction and positive in the y direction. But I mean, that should be pretty obvious based on just looking at the problem and seeing what you're looking for. So again, this is just, we're going to call that A. So draw the free body diagram of the entire thing. Okay, so again, like I said, this is going to be a 3, 4, 5 triangle here that A is at. And we have our P and our two reactions here, dy and dx. So again, you can basically just solve this the same way we solved the last problem. So sum of the forces of y is going to be 4/5 A minus P plus dy is equal to 0. Sum of the forces in the x is equal to dx minus 3/5 A is equal to 0. And then our moment, we'll solve everything else here. So moment about D is equal to, our P is causing a positive moment, and each of the other components of A are causing negative moments. So negative 3/5 A times 2A minus 4/5 A times 2A is equal to 0. Cancel out all these distances A here, and now we can just move both of these terms to the other side to get P in terms of A, and then divide through to get A in terms of P. So that's going to be, what is it, 6/5 plus 8/5 is 14/5. So we're going to be multiplying by 5 over 14. So A is equal to 5P over 14. So again, just cut at J and draw a free body diagram of that section. They just scroll down again a bit so I have more room. So again, this is section JA. I'm going to have an axial force, a shear force, and a moment. And then we have this force here, which we said is 5P. Sum of the forces in the x is equal to V minus times 5P over 14. 0, V is equal to 3p over 14. Our sum of the forces in the y is equal to F plus 4/5 times 5p over 14 is equal to 0. So F is equal to 2p, sorry, negative 2p over 7. And then our moment. So some of the moments about point A is going to be negative A times this V value we got, so it's 3p over 14 minus P, or minus M is equal to 0. So M is just negative 3pa over 14. Okay, so on to the next problems. These ones are again fairly similar. But the difference here is that our roller and our pin joints have switched places, and this is actually going to create quite a bit of a change here in terms of how these this load P is supported by these two pins, and it's going to change the internal forces at J. So in this case, it's pretty simple since the roller is just supported from this section here. We know it's just going to lead to a vertical force, which we'll call Dy, and then there's going to be two forces here, Ay and Ax. And then there's going to be a load P there. So now some of the forces in the x is just Ax, which is equal to 0. Some of the forces in the y is equal to Ay plus Dy minus P is equal to 0. And then our sum of the moments, we want to take that about point A. Or actually, you could take it either way because Ax is 0. So let's take it about point D. So we're going to get a positive moment due to P, so P times A. And then a negative moment due to Ay. Ax is 0, so we don't need to count for that. So minus Ay times 2A. This is equal to 0. So again, cancel out the A's, and then we have Ay is equal to P over 2. So now that we have that, we can simply cut the beam at J and solve for our internal forces here. So we have our this is our axial force, our shear force, and our moment. And then we have just Ay acting here. And we said this was P over 2. So our sum of the forces in the x is just V, which is equal to 0. Sum of the forces in the y is equal to F plus Ay is equal to 0. So F is equal to negative P over 2. And then our sum of the moments about point A is just going to be V times A, But since that's 0, this just goes to 0. V is 0, so the whole term goes to 0. And then minus m is equal to 0. So this is just telling us m is equal to 0. So if we look back and compare that to this problem here, here at point J, we didn't get an axial force at point J, but we did get a shear force, and that shear force led to a moment at J. So when you switch around the two, the pin joint and the roller joint, it leads to sort of the opposite case where you end up with an axial force but no shear force, no shear moment, or no moment due to that shear force. So shows how changing around your supports actually does have a big effect on the internal stresses within the beam. So moving on to part B, now we have roller supported at an angle. So we want to figure out what angle the force due to the roller is going to be at. So again, it's going to be perpendicular here with a 3, 4, 5 triangle. So we again want to write the slope here. The slope is 4/3, it's going up 4 and over 3. And then to get the perpendicular to that, we just say it's the opposite reciprocal. So negative 4/3 inverse. And this will be a e over negative 4. So drawing that on here, we're going negative 4 up 3. So now we can do a free body diagram of our entire structure here. So we have this force P acting down. We have this force, we'll just call it D. This is going 4 over and 3. And then we're going to have two reactions here. We'll call them AY and AX. So when we do our forces in the X, we get AX minus 4/5 D equal to 0. Sum of the forces in the Y will give us AY minus P plus 3/5 D is equal to 0. And then our sum of the moments, we want to take about point A since there's two unknowns there. So our sum of the moments about A will give us, let's see. So this force here, P, is going to give us a negative moment because of the right-hand rule, so negative A times P. Let's see. And then each of these components of D are going to give us a positive moment. So we're going to have plus 2A times 3/5 D plus 2A times 4/5 D is equal to 0. So again, cancel out all these distance components, and then we have simply formula for D in terms of P. So that'll tell us D is equal to 5P over 14. Okay, and so when we plug that back into this first equation here, we're simply going to get AX is equal to 2P over 7. And then plugging it into our second equation here gives AY is equal to P over 14. So now that we have those, a free body diagram of the AJ here. So let's just draw it like this. So we have this is point A, point J, and we have AY was 11P over 14. AX was 2P over 7. And then we're going to have our axial force, our shear force, and our moment. So now that we have all that written out, we can just do our sum of forces in the X is equal to B plus 2P over 7. This is equal to 0. So B is equal to negative 2P over 7. Our sum of the forces in the Y is F plus 11P over 14 is equal to 0. So F is negative 11P over 14. Finally, our sum of moments about point A will give us a negative moment due to B, so negative A, but then B is a negative force, so this is going to turn out to be a positive, and then minus M is equal to 0. So this will simply tell us M is equal to 2AP over 7. And now I want to draw a comparison between this problem and the next problem. So here we have this force, or this, the force due to this roller pin is up and to the left. And that's obviously supporting this downward force. But if we have a problem where it's like this, it is not supporting the downward force. It's actually pushing down on the roller itself, or the roller is pushing down on the beam, adding to this force. So how is this supporting it? Well, if we're looking at point A, this is creating a negative moment. The downward force here is creating a negative moment, but then we have this side force here that's going to be creating a positive moment. So overall, this load, or this roller here, is going to be countering the moment and keeping this static. But how is that going to affect the stresses here at J? So just keep that in mind as we go through the problem. So let's first draw out what this force is going to look like. So we have this 3, 4, 5 triangle with the force going like that. So if we're drawing the, or if we're writing the slope here, it's going to be going up 4 and back -3. The perpendicular to this is going to be the opposite reciprocal. So this is just going to give us a positive 3/4. So up 3/4. Okay, so now that we have that, draw our free body diagram. This force P, and now we have a different force here, D, which we just said is a 3, 4, 5. And then we're going to have our two reactions here, AY and AX. Sum of the forces in the X is AX minus 4/5 D is equal to 0. Sum of the forces in the Y is AY minus P minus 3/5 D is equal to 0. And then our sum of the moments about point A will give us, okay, so again, this P is creating a negative moment and it's A distance away, so AP, and then we have, now the difference here is that one of the forces, or one of the components of this D force here is creating a negative moment, and the other one is creating a positive moment. So we have to figure out which one is which. Now, if you look at a right-hand rule, you'll see that the vertical force is creating a negative moment. So let's write that. So minus A, sorry, it's 2A times 3/5 D. And then we have plus 2A times 4/5 D. So these two moments are actually countering each other, and that's going to lead to D having to be bigger to account for this P force, or to correct this P force. So we cross out all these A's, and we end up with, let's see, so this ends up telling us D is equal to 5/2 P. Now again, let's look at that in relation to the last problem. Here, D was only 5/14 P, so it's less than, or almost 1/3 of P, whereas here, it's 2.5 times P. So even though you have the same force acting on this beam, you're having to apply a lot more force at the reaction to counteract the moments due to the force. So now that we have that, we can plug that into our other equations, and this will give us, let's see, the first one gives us AX is equal to 2P. So again, a fairly large reaction there in comparison to our last problem. AX was 2P/7, so it's 7 times as large as the last problem. And then AY is 5P/2 as well. Versus 11P/14. So again, it's almost tripled, I think. Which makes sense because we have this large D force here acting down, and it's just adding up to more force that AY has to counteract. So now we have to look at how that's going to affect the internal forces at J. So we have axial, shear, and moment. And then we're going to have this large AY force here of 5P over 2. And a large shear reaction here of 2P. Let me just scroll down a little bit so that I have more room. So our sum of the forces in the X is equal to V plus 2P, which is 0. P is equal to negative 2P. Our sum of the forces in the Y is going to be F plus 5P over 2 is equal to 0. F is equal to negative 5P over 2. And then our moment. This is where we get a very large difference. So again, we have a negative moment due to P. Sorry, I mean a negative moment due to V, and then a negative moment due to M. So this tells us M is equal to 2AP, whereas in the last problem, we had, let's see, I believe it was 2AP over 7, yeah. So again, 7 times the internal moment there. And that's going to create, a lot of energy within the bar. And that's not good. That means this isn't supported as well. It's more likely to break if you're not considering it as being statically or being a static beam. So it just goes to show the difference between how these reactions, their effect on the internal forces within a beam. So now I'm going to have to find another problem. We still have a bit more time. I want to do a distributed load problem. So let's see. Okay, so we're going to try a problem here, 7.45. So in this problem, it's a bit different from some of the stuff we've done in class. So we have a beam here, but the beam is sitting on the floor. And so the fact that the beam is sitting on the floor, when we're doing a free body diagram of this, is actually meaning that the floor is having a distributed load across the entire beam. And then we also have distributed loads on top of it. So call this point A, call this point C, or point B, C, and D. And we're told what these reactor, what these loads are here. So this is 3 kips per foot on each of these. So that's on both of these. And then we're also told the dimensions here. Okay, and so we're told to assume that the upward reaction of the ground on the beam is uniformly distributed. And so they want us to draw shear and bending moment diagrams and to determine the maximum absolute values of the shear and bending moment. So this is something you'll be in future classes that aren't dealing with statics, because you want to determine where the highest stresses are. So of course we want to do a free body diagram of the entire beam. So now we're going to have a distributed load here at the bottom. And this is uniform, so whatever it is, we'll just call it, I guess, WG. So this is essentially the distributed load due to gravity. And then we still have these distributed loads on top. And so simply to determine WG, all we're going to do is take some of the forces in the water. Okay, so this is going to give us, all we're doing is we're taking the magnitude, the actual location where the force is acting. Like if we were to draw, this is going to have some resultant force there, and each of these is going to have some resultant force, but we don't care about the location right now. All we care about is the magnitude. So to get the magnitude, it's pretty simple. You're just multiplying these values here, this 3, times the distance over which they're acting. So this WG is acting in the positive direction, and it's acting over a distance of 12 feet. So WG times 12. And then each of these other forces are acting at a distance of 3 feet, so minus 3 times 3, minus 3 times 3. And this is just going to be 0. So WG is equal to, what is that, like 18 over 12, so that's 1.5. And this is going to be in the units kips per feet. So now what we want to do is just cut the beam at different locations. So here, there's one distributed load there. Then we have a different load here and a different load here. So we're going to need to cut it in 3 different spots. We want one there, and one there. And then we can determine the internal reactions there. So we're just going to say this is from A to B. Okay, so this is point A and this is point B. So there's going to be a shear force and a moment. Okay, and then we have, obviously, we still have these distributed loads on top. And on bottom. Now these distributed loads, as we just solved for, are not equal to each other. So that's still going to create a moment here. So again, our sum of the forces in the y is going to give us 3 times, and now we don't know what this distance where we cut it is. We just say this distance is x. Okay. So for now, just don't know what that value is. We're just this in terms of the distance away from A. So x is just whatever distance measured from A. So 3x minus 1.5x. Okay, so that's the forces due to these distributed loads. And then plus v is going to be equal to 0. So this tells us v is equal to 1.5 x. And that's only true between A and B. So now we want to do our moment equation. And we know that these resultant forces are going to be acting, since this is a uniformly distributed load, we know they're going to be acting halfway through. So we can just call that distance x over 2. So the moments about A are going to be what we just said before. So it was 3x, but then multiplied by a distance of x over 2. Oh, I'm sorry, I just realized I made a slight mistake before. This is actually supposed to be negative, and then this one is positive. So that makes a positive E here. Okay. So that negative force creates a negative moment. Oh no, sorry, it does create a positive moment. Let's see. Let me think about this. Yeah. So if you're doing a right-hand rule, it's going to create it's going to create a negative moment. The other one is going to create a positive moment. So negative 3x. And then the other distributed load is going to create a positive moment. So plus 1.5x times x over 2. And then this m here that I drew it negative, so we'll just say it's minus m is equal to 0. Okay, so simply we can write this as m is equal to, let's see, it's negative 3x squared over 2 plus 1.5x squared over 2, so that's negative 1.5x squared over 2. Now, once we're ready to graph this, we can just plug in our values at the endpoint, so at 0 and at 3, and that'll tell us what the values for these are. But for now, I'm just going to leave it in terms of x. So let's just scroll down to give us more room. Actually, I'll move on to the next page. So now we want to draw from point A to the next cut. So our next cut is going to be between point B and point C here. So again, we're still measuring x from this point A, but now there isn't going to be a distributed load throughout the entire section here. Okay, so now that we can draw our next free body diagram, we're going to have a distributed load throughout the entire bottom as usual, but only part of this top section here. So now we know what this distance is. Distance here was 3 feet, and we know the entire distance is x. So now we can draw reactions based off of that. So this reaction here is going to be 1.5 feet away, and then the reaction, sorry, I meant to draw that at the top, up here. This is 1.5 feet, and this is x over 2. But when we're doing our sum of the forces, we can't do that. That's only going to be useful for our sum of the moments. So our sum of the forces in the y is going to be, oh sorry, we have a V, we have our shear force here, and our moment. Okay, so again, the reaction due to this first force here is just going to be 3 times 3 feet, and it's in the negative y direction, so we draw it like that. And then this other here is going to be positive 1.5, but that's times a distance. And then we're going to have plus v. Okay, so this is telling us between B and C, our V value is going to be 1.5x minus 9. Other way around. 9 minus 1.5x. So now we have some of the moments about point A, and this is where we use these values here. So we know that this 9 force is going to create a negative moment. So it's going to be negative 9 times the distance 1.5. So that's the moment about A due to that. And then plus this other force here, which we said was 1.5x. And this is creating a positive moment at a distance over 2 away. And then we're going to have minus m is equal to 0. So m is equal to, what is m equal to? So it's 1.5 x squared over 2, 0.75 x squared minus 9 times 1.5, which is what, like 13.5? Is that right? Sounds right. Okay. So now we have our other two equations here, and then we just need to do one more similar to this, and then we'll have all of our equations. So finally, we have one distributed load, a second one. This one is not the entire distributed load. We're not taking this to the end. This is in between. But again, there's still a distributed load along the entire bottom. Okay. So this distance, the distance to the center of this is still 1.5. And now it's going to be a bit tricky to figure out what this distance here is. So we know this entire distance is length x. We know the distance from here to here is what? Let's look back for a second here. It was 9. So knowing that, we can actually write what this distance here is in terms of x. So the distance from A, which is over here, to the center of this is going to be, let's see, it would just be x plus 9 over 2, right? Because it's basically just the point in between this 9 and x. So the distance from here to here is just going to be x plus 9 over 2. Or you could also write it as x over 2 plus 4.5. This is just one way of writing it. So now that we have that, we can do our sum of the, we need our shear force and our moment. And also, these are just the standard ways of writing the shear force and moment. Shear force is always drawn as acting up. If it's not acting up, then we consider that negative. And then the moment is always drawn in the negative k direction or clockwise. And so if it's in your diagrams of the shear force and moment, if either of those are negative, it's just you're thinking of them as acting counterclockwise or downward. But these are the conventional ways of writing it, so you want to keep it that way. Some of the forces in the y is going to be this 3 times 3, which is negative, and then now we have another 3, or minus 3, times this x minus 9. So that's the length here, the length of this section here. So that's going to have a magnitude of 3 times x minus 9. Okay, and then we also have this plus 1.5 times x, and then plus b is equal to 0. So we gotta simplify all this out a bit. So that we're gonna end up with what? It's gonna be b is equal to 9, 3x minus 1.5x. So what is that? Plus 1.5x, and then plus or minus. This is going to create a minus 27. So this is just the same as writing 1.5x minus 18. Yeah, I believe that's right. I'm just kind of doing this off the top of my head. And then are some of the moments about point A. So we have this distance 1.5 times the magnitude there, so it's going to be negative 9 times Sorry, let me just check again. Yeah, so this is going to create a negative moment, so it's negative times 9 times it's 1.5. This one, again, always is going to be the resultant force is x over 2 distance away, so, and that's going to be a positive, so plus 1.5x times x over 2. And then finally, this other term here is going to be pretty big. It's going to be minus our, what did we say before? 3 times x minus 9. So that's the magnitude, and then the distance is x plus 9 over 2. Now, I'm sort of out of time here. All you have to do to finish this problem is simplify this equation out. Oh, sorry, there's also going to be minus m here is equal to 0. So you would simplify this equation out, and then you would graph it between the points that you're given. So we know between x equals 0 and x equals 3, this is going to be the equation for the moment, and this is going to be the equation for the shear force between x equals 3 and x equals 6. We have this value and this value, and then between x equals 9 and the end of the bar, what was it, x equals 12, we're going to have whatever the resultant from this is and this. So that's pretty much it. Let me just stop the recording.